Okay, ready to start. Our next presenter, Dušan Zamurović from Kazumo, will tell us a bit more about smart pipelining, reactive approach to computation scheduling. Dušan.
Hi, everyone. So, before I start, Kazumo online gaming company, it's a Swedish company based in Malta, for obvious reasons, right? And so the topic of this talk is smart pipelining, a reactive approach to computation scheduling. But before we start with that, blockchain, right? Well, no, I'm not going to talk about blockchain, so it's everybody else does, so we can skip that, right? So I joined Kazumo in June 2016, and we didn't have a data team at that moment. And yeah, I didn't mention I'm working as data engineer in Kazumo on building in-house big data platform, right? And this was how it felt like last 2 years or so in Kazumo, because Kazumo is a company that started in 2012, and you know, the customer base grew and the business grew and everything went pretty much good. And then we came in with an idea to build a big data platform and finally, you know, build on top of the data that Kazumo gathered along the way. And we had to pay additional attention of not breaking anything inside of the company, right? So we didn't have exactly a possibility to make an error. So that's why I'm saying, and the biggest growth in Kazumo in customer base and the number of players playing it happened in last year and a half. So this was how it looked like. You know, a car that is accelerating and us doing something in the background, changing tires and that kind of things. When we talk about Kazumo and Kazumo in general, the product, I like to split it in two parts. The first part is gaming platform. That's basically a casino platform. That's where the games are happening, where the games are integrated from other gaming providers, and where players are making their deposits and doing their withdrawals and making their bets and hopefully winning some wins, right? And that gaming platform is microservice architecture, heavily domain-driven design, implemented CQRS, of course. And by the way, there was a nice presentation about CQRS event sourcing just before this one. And the gaming platform is implemented in polyglot way. So what guys have over there are Java, Scala, Python, Kotlin, shell always as glue, and yeah, you know, expected stuff. And then the other part is big data platform. That's where team I'm working in comes from. Does anyone know what that thingy over there is? Okay, good. It's always interesting to tell that story. So before 2016, there was only one data scientist, data analyst in the house, and how he did the analytics and how he was sharing the insights was, you know, just dump the data to his local laptop and do some magic over there, and then prepare a presentation or PDF with slides or whatever, and then those assets were floating around the company, and clearly it was not the best case. And then when we came in, the decision was that we are going to build that big data platform in the cloud. We said, okay, we have first of all to move 5 or 4 years of data into the clouds before we actually can do some computations on it. And we discussed it, and you know, Malta being an island, internet is not the cheapest thing over there. And also there was a happening that one of the ships, when the ship just you know, well, parked itself in front of the island and dropped the anchor, it cut off the cable, and yeah, it happens. So we calculated that we would need 2 months of bandwidth maximized to get all the data from multi-data centers to the cloud. So clearly not the way to go. So what we did is we changed the format of the data, and we compressed it, and we shipped it physically. And this is where this little thingy comes into story. That's Amazon Snowball. That's a thing that you ask for Amazon to send you. Then you take it to your data center, you plug it in, you get the data to that thing, you ship it back to Amazon, and then after some days your data appears in AWS 3, which is quite cool, right? So we are saying that we actually brought the snow to Malta, right? And in regard with the data platform, some fun trivia. We are dealing with 36 billion of events in total. So in this moment, it's very important to mention that when I'm saying what I'm talking about here, this is data that is coming only from a gaming platform. So that's only what is produced in casino part of the product. I'm not talking about data that is coming from integrations with third-party APIs like Facebook or DoubleClick or whatever. This is just data that comes from our players. And data is around, daily data is around 40 to 50 gigabytes. And that roughly translates to 60 millions of events per day, which is interesting enough because some months ago I gave this talk in a similar talk in Novi Sad, and the numbers were lower. Numbers were around 50 million. So we are still growing over there, and hopefully we will grow happily ever after, right? And this is how it looks like. This is only the graph from the beginning of 2014. I cut off the 2013 and 12 because it's not very important for the presentation. And I like to. This is also a cool story. This little drop over there, that's a bug in the registration form. And yeah, our affiliates weren't very happy with that. And this is how the current data flow looks like. So we have the big square represents the Kazumo gaming platform, and that's where the microservices are living. And those microservices are, they can be whatever you want. It's like, I don't know, anti-money laundering service that is taking care of some checks in the background, some verification services, some wallet services. So it depends. The real functions of those services can be anything. And those services are communicating over RabbitMQ, right? And there is also one service that I extracted. It's creatively called Big Data Service, right? And that Big Data Service is listening to all the events that are happening in RabbitMQ. And it pushes them to AWS Kinesis when we are, where we are using it through the Lambda functions, we are pushing those events to S3. That is how we are creating our data lake. And this is, let's say, an overview of what we are using from AWS services. So in the upper part of the picture, you see the third-party integration. So it's Salesforce, it's Facebook, Mixpanel, MediaMath, whatever. Doesn't even. It's not super important for this. On the left, you see Kazumo. That's the gaming platform. That's where the things are happening, right? And then data comes through Kinesis, as I explained. Through Firehose Lambda, it goes to S3. Then when data reaches S3, we are firing SNS notifications to activate data pipelines. This is now where the orchestration is happening, and this is what the topic of the talk is. So we are activating data pipelines to activate EMR jobs, EMR computations. When those EMR computations do their thing, data is being pushed back to S3, for example, or being pushed into Insights. That's our in-house product. And from the S3, data is being pulled into Redshift. That's Amazon warehouse solution. And then from the Redshift, we are taking the data and pushing it into Sisense. That's a BI solution and that's what is used as our self-service tool in the company. So basically, everybody has access to Sisense and the cubes, and they can do. So people from marketing can have access to the data and can do the checks and can do the cross comparison or whatever they need. So a bit more about Amazon data pipelines. Is there anyone in the room who is actually using AWS pipelines? Okay. So for some reason, it's not very popular Amazon product, but I love it. It really solves a bunch of issues for us. So data pipelines is a service that provides you an option, provides you a way how to orchestrate your things, your jobs. So this particular one has some configuration on its own. That configuration can contain information, for example, like you should run every day at 1 o'clock, for example. That's the most trivial part of that configuration. It waits for something to happen in S3. After that precondition is fulfilled, it runs EMR activity, and after that, it triggers the shell command activity. Basically, shell command activity, you can think of it as just running a shell script, and that shell command activity is pushing a file to S3 back. If something goes wrong, SNS alarm is activated, and we are getting a message in our team Slack channel. This is a very simple one, and now you can ask, okay, but here we have EMR activity, and where the EMR activity is happening, it's happening in the EMR cluster, which is somewhere behind. So we are using, in this particular case, we are using a cluster that is always that is already started, and we are expecting it to be running at the moment. But this one, okay, so it's not. We can't see very well, but this is another pipeline configuration, and it's much more complex. But of course, I will not go into details. But I just wanted to present that pipelines can do some serious things, and will help you really much a lot with orchestrating jobs and building dependencies between jobs. Now, the real problem that we're solving and that I'm trying to address in this talk is orchestration, because at one moment we realized that we are fighting not computational problems. We are not fighting anything like that. We are fighting against time, because all of those computations are happening at the moment. They are happening during night. So those are daily computations. We don't have, at the moment, we don't have a need for anything to happen more often. So in order to perform daily calculations, we have to wait for the previous day to end, right? So we are bound by that boundary. We have to wait the midnight of a previous day, right? Now back to Sisense. Sisense is BI tool, and it needs some time to build the cubes. So basically, to get all the data and get it into its memory so that people could use it in the morning. So a little bit of reverse engineering. People start working at, let's say, 8 a.m. and Sisense needs roughly 3 hours to build that with the amount of data that we need. So Sisense has to start with building those cubes at 5 a.m., which leaves us with roughly 4 hours of computation time, right? Because some of the data centers and the data is in Malta. We can't actually start performing our computation in UTC time zone. We have to wait for Malta time zone, and we have limited time. And then daylight savings time skips in, and sometimes it steals another hour. So we had to be really clever about this. And then, so we are limited by time, right? And then there are jobs that depends on some other jobs. So you can't really just, our initial solution to this was, yeah, let this guy run at 1, and we hope it's going to finish before 2, and then we are going to be a little bit defensive, and we are say that this one, which depends on the previous one, is going to run at 2:05 or something. and then always something happens. This is distributed system. Something always fails, something always goes wrong, something gets slower. Then you started too early and the data wasn't complete, and then you think everything was okay, but then at noon next day somebody from marketing comes and say, hey, something's wrong with data, and then you realize that data was not complete because the computation before wasn't finished at the proper time, right? And then we came up with the solution that I'm going to present here using AWS data pipelines and job scheduler Lambda. So how it goes. The precondition number one is that all of the computations have to be idempotent. What does it mean? It means that if you run one computation once, the results that you get are going to be the same that if you run that computation again and again and again. And all of our computations, as I said, are daily basis. So if I run computation for 6th of June last year, and I run it again for 6th of June of last year and next year, I want to have the same results for 6th of June. And all of our target table in Redshift or in Hive are partitioned by day. So basically that gives us the option that we just overwrite. We delete the partition and we overwrite the partition with the new set of data. With those preconditions in place, we have this kind of solution. CloudWatch event comes first. That's the only hard-coded thing in this solution. This event is something like firing an SNS notification at, let's say, 1 o'clock or something like that. So basically, that's when our chain of computation is starting. And this is, we are firing at that time. As I said, we are waiting for the previous day to end. That CloudWatch event is triggering a Lambda function, something we call scheduler Lambda. That Lambda, based on the type of the event, knows that, oh, this is CloudWatch event. I know this is the beginning of our computation chain. And I am going to trigger the first job in that computation chain. It triggers data pipelines. First data pipeline that comes in our dependency chain. That data pipeline does its job, and after it's finished, it pushes empty file to S3. That's one little thingy that you saw on the simple configuration example. Pushes empty file, and that empty file has we have a naming convention for that file. It's saying name of the pipeline that actually just finished, date when it finished, and possibly the hour of when it finished. Not when it finished, but the date of the data it was performing on and the hour of the data that it was performing on. So basically now we know by this example in green that the job that is named row to JSON finished working on data for, I have too much zeros over there, but finished performing work on 17th of February 2018, and it was hour number 3. So we just processed the data between 2 a.m. and 3 a.m. When that is done, creation of the file in S3 is triggering SNS notification that is configured on the bucket where we are writing down those files. And that SNS notification triggers the same Lambda that we triggered before. And now this Lambda comes again and says, oh, this is not CloudWatch event anymore, so this is SNS coming from S3. And I go to my dictionary, to my, let's say, a map of dependencies. And if row to JSON job finished, in that dictionary, I have the list of events, the list of jobs that I should trigger and activate. In case something goes wrong, there is SNS notification to the team channel, right? And we have a message like this saying that row to JSON transformation finished with 96 errors or whatever. And then we try to fix things, right? And this is how the code is looking like. It's fairly simple, to be honest. And I think the biggest Well, the biggest thing of this approach is actually that we didn't have to do a lot of work. We just nicely incorporated all the services that Amazon provides. And yeah, people usually ask me like, why you're not using, I don't know, Airflow, or why you're not using anything like that, because there are open source frameworks for this. We are not using it because in order to use those things, we have to install them, we have to configure them, we have to maintain them. This, we don't have to maintain. We don't have any infrastructure with this. The only thing that we have is one EMR cluster that is running like always, it's always up. It has a master node and 2 data nodes that are nothing. They are just standing there because without data nodes you can't have a cluster, right? And we are calling that cluster, we were calling it a long running cluster, but then we realized it lacks personality, right? And we want to have it, you know, forever, that it's always up, always flawless, right? So we renamed it to LeBron cluster. And basically, when you come to office at 8 a.m., we don't have any infrastructure. There is nothing, only that small little cluster. If you pay attention to what is happening during the night, then we have like 6 clusters of 20 nodes, 30 nodes, 10 nodes, I don't know. When those clusters finish with what they are doing, they shut down. And again, at 8 a.m., there is no infrastructure. So we are kind of serverless, right? And we are not maintaining that at all. Amazon does that for us. So this is the dictionary of our job dependencies, right? And you can see over there, the CloudWatch event. What is happening when the CloudWatch event comes? It's the split events. That's the name of the job, right? And then when the split events is done, when we receive the notification from S3, when split events is done, we are starting with computation of player entry or whatever else, right? And we, of course, have some situations in which when, for example, block players log computation is done, we are not doing anything after it. And how we are doing it, it's a simple Lambda function written in Python using Boto3 library. I think it has less than, I don't know, 200 lines of code, maybe even less, I'm not sure. We are just using Boto3 to instantiate the data pipeline client. We are asking our Amazon which are the pipelines that we have. Just give us the list of the pipelines that we have defined in this particular moment, right? Then we search for the pipeline with the given name of the job that finished. Now this is something that we had to do because you have to, Amazon lets you instantiate 2 different pipelines with the same name. And then you have to be careful about that. So if you have 2 pipelines with the same name, this is not going to work. You have to take care of that. And taking the name of the pipeline, we are by the name, we are getting the ID of the pipeline, and we are providing the ID of the pipeline to the call of the API to activate the pipeline. And it's, I think that's it. Now, what is for us in the future? We want to be more event-driven, because now, at this point, when the last data pipeline finishes its computation, that's where our automation stops. We have a separate script that runs the Sisense cube builds, and we want to automate that also. So we want to, and what's wrong with that? Because if something fails during these computations, the cubes are going to be built nonetheless. And we don't want that, because what we want is to save the computation time, and we want to skip the computation of the cubes if there is no data, if we screwed up something during the night. What we implemented as a substitute to that, we have when something goes wrong during the computations here, there is a notification that goes to Sisense, and then Sisense switches the notification in the like a toolbar of the web application saying, data is not correct for the day that and that. Please, make note of it, so that people who are actually using the data know that we screwed up during the night, right? Remain serverless. That's what I just explained. We have almost no infrastructure to maintain. Data pipelines, they sit in Amazon, and I don't even know which computers are there. You can, in data pipelines, you can configure the type of the instance that is going to run your activities and your jobs, and you configure the EMR clusters that are going to do that. So basically, while the pipeline is not running, there is no computer living, right? Lambda functions are serverless per se, so I don't even know which are computers that are running those pipelines, those lambdas, and yeah, that's it. So we don't have to maintain anything. Yeah, grow self-healing, that's something I wish we could do, and I hope we will do it, because right now we are consuming the live stream of the events that are coming from RabbitMQ, as I described. I believe that a live stream of events is good for certain things. It's certainly not the best option when you're dealing with financial data. Because if that live stream has a glitch, you have to have a backup, you have to have alternative source of data that is coming to your data lake. And we are working on near real-time data feed, because we didn't, so far we didn't have the proper use case, but I think guys are working on game recommendation engine for players that is going to consume real-time data feed. And that's basically it. Yep. Thank you very much. So any questions, please fire. I guess that's no questions, right? Okay, thank you.